Hello and welcome again to Functional Programming course, and we shall continue talking about lists, and we will talk now about higher order functions. You have seen already that manipulating lists follows some kind of common pattern. So almost always when we have the recursive function which deals with the list, we decompose the list into head and tail, and then we do something with it. So let's consider the first kind of possible tasks, which is when we want to find some kind of aggregate value from the list. For example, we want to find the sum of elements, product of elements, or minimum and maximum elements of the list. Those kind of functions, they are defined in a very similar manner. For empty list, we return some initial value. For non-empty list, we apply some function to the head of the list and the tail of the list, the result of applying our recursive functions to the tail of the list. So this pattern can be extracted into some higher order function. And when I say higher order function, it means a function to which we can pass another function. In which case, if we want to unify those two functions into some more abstract one, we need to pass the operation. Should we add or should we multiply? Um, if we are talking about the finding minimum or maximum value of a list, for example, it works the same way. If it's an empty list, we return some kind of value. If it's non-empty list, we apply some function. In this case, it's a function max to the head and the tail of the list. So this can be abstracted using more abstract function called fold. So when we fold a list, we pass the function f, which is applied to accumulator and some element, and we pass the initial value of I. And that as the function looks exactly like the ones we have seen before with the sum and product, but it's abstracted away using this f. So when we have an empty list, we return this initial value I. When we have non-empty list, when we have head and tail, we apply function f to head and the recursive call of the function on the tail. So if we define this function f as this at sign, we essentially compute this expression. We first, like, this recursion goes deeper down until the end of the list, and then it applies the function to I and nth element of the list, and then the result is applied to n minus first element of the list, and so on, and finally it is applied to first element of the list. So this is essentially like the intermediate values. They can be thought of as accumulator, and this accumulator goes through all lists and is applied to all elements in turn. So if we want to define our function sum, our function sum would be the fold with operation plus and initial value 0. The product of elements in the list would be a fold with the function multiply and the initial element 1. Max element of the list would be the fold with the function max and the minimum value of an integer. So this fold can be used to define many different functions. If you consider typing, the typing of this function fold is the following. We pass the function f, and the function f takes this t is the type of element lists of elements of the list, and then a is the type of accumulator. So it takes the accumulator and it returns accumulator, and it takes the initial value of accumulator and the list and returns some resulting value. So there is also another function very similar to fold, which is called reduce. And reduce is useful when you have accumulator of the same type as the elements of the list. So for example, if you want to add all elements of the list together, sometimes it's not necessary to start with some kind of initial value 0. You can start, for example, with the last two elements of the list, add them together, and then add that to the previous element, and so on. So this function is called reduce. In terms of if we were defining those functions without any like high order functions, you see, we can start with the minimum value, or we can start with like the first value of the list, and that is the difference. We don't need the minimum value. So this reduce operation is useful when we want to perform like pairwise operations on the values of the list. So this kind of definition, max L equals reduce max, looks neater than this one, max L equals fold max in 32 mean value. However, reduce cannot always it cannot deal with the accumulator of a different type. So let's again switch to examples. Suppose I have the list and I want to compute both minimum and maximum element of the list. So I want to define function called min max and of L. So one of the ways to define this function would be to say list reduce min L list reduce max L, which would be kind of a nice way to define it, but not very effective way, because we need to go to pass through the list 2 times, right? What can we do if we want to pass just once? Well, we can define the same function min max L using fold. We can say list.fold, and then accumulator would be it would have it would not be the simple value. It would be the pair of minimum and maximum value. So the function, the fold function, would accept this accumulator pair and the current element x. And what it would return? It would return minimum of me and x and maximum of me and of may and x. And then we start with int slash int dot. So we start with int 32 max value, int 32 mean value. And that is another way to define the minimax functions. Okay, I probably need to dig and find the right way to define that, but we can say this equals to 1000 and this equals to minus 1000, for example. And this is much more effective because it does just one pass through the list. So the interesting thing is that the accumulator in the fold function can be anything. It doesn't have to be a simple value. It doesn't have to be the same type as the elements of the list, and it doesn't have to be simple at all. Another types of operations is called map. Suppose I want to compute the sum of squares from 1 to 100. The simplest way to do that, to compute the sum, we know we can use fold, but how do we come from the numbers from 1 to 100 to the squares of those numbers? This is exactly what the map function does. It applies a given function to every element of the list. So if you want to define map, you would do it like this. You can say, okay, with the empty list, it's an empty list. If it's a non-empty list, you apply the function f to the head, and you do the same with the tail. Map can also be defined in terms of fold, because as we mentioned, in fold, accumulator doesn't have to be simple. Accumulator can be another list, in which case we would take the list element by element, and we would append the f of h to the beginning of this list. So map is a very interesting concept, and let me start let me actually quickly describe you how we can think of map as a function which lifts certain operation to another type. That is something we will talk about later on when we talk about category theory and the beauty of functional programming, when we think with higher level abstractions, but that would be the first step to think in this direction. So suppose we have the type string and type int, which is represented by those dots here. And there is a function length which maps every string to the length, to its length, to an integer number, right? So this length maps one domain of strings to the domain of integer numbers. And then for each string, we can have the domain string list, which is higher level domain, right? And like for every type in our program, we can have the list of values of this type. And this is something called functor, when we map types to another types. So we have the functor which lifts strings into lists of strings, And we have the same functor which lifts integers to list of integers. And what map does, map lifts this length function to the domain of higher order abstractions. So the map of length is a function which maps from string lists to integer lists, right? You can think of it like you can use map in other types which you can think of as mapping. For example, there is optional type. Optional type is when we have a certain value and it can be either a value or none, right? It's the type which we want to, for example, if our function can return error or integer number, we would return the optional type. And we can think of this option as also as a functor. So it would be like for every type in F# program, there is also an option type corresponding to it, like string option type and integer option type. And suppose I want to map the function length from option string to option int. How would it work? So option string can be either a string or the value none. And I want to compute the length. So naturally, if the input string is a string, which is sum of x, I would return the length of the string. And if it's none, I will return none. And this map, we can call it fmap, for example. It would also lift the function length to a different domain, to the domain of option types. You can see the similarity. This allows us to kind of think at a higher level of abstraction even than maps. So we can say that for any type, if we have some kind of types which are composed of it, lists, option types, or something else, we can build a function map which from all functions in the original types builds the corresponding function in the dependent types. So that is a little bit complicated probably at the moment. So let's think about this a little bit, but we will come back to talking more about those kind of concepts when we start talking about category theory, monads, and those kind of things. One more function which is really important is called filter. So for example, I have the list of web pages, and I want to see how many of those web pages contain the word MIPT. How many, for example, home pages of leading universities in Russia contain the word MIPT. So how can I do that? Here is my list of resources. First of all, I need to download them, and meaning that for each address, I want to return the contents of the page. And this can be done using map. I can say list map HTTP request, and it will download the page. Then, how do I filter the pages which contain the word that I need? This can be done using list filter. So list filter accepts a predicate, in which case the function which returns true or false, depending on whether the page contains the word MIPT or not. And then I just calculate the length of the resulting list. And the filter can, of course, be defined in this obvious manner. For empty list, I return the empty list. For non-empty list, I see if it's if the predicate is satisfied, then I return this element. If it's not satisfied, I return the tail. This can also be defined in terms of fold. As you can imagine, fold is kind of a universal operator which allows you to traverse a list. Many of those things can be written in a simpler form, which you may know from Python. If you have learned Python programming language, it uses this kind of list comprehension operations a lot. So initially, suppose I want to construct the list of powers of 2. So the library function to do that I can use, which it's called listinit. I can say listinit 9, meaning from 0 to 8. And then for each x, I return 2 to the power of x. But the same thing can be written in the nicer way. I can say for x in 0, 8, return 2 times float, 2 to the power of x. And you can imagine that this is very similar to mapping, because what I start with is the list from 0 to 8, and then I, for each number, return the power. So you can view this as list map, and then I apply some function to each element. So in fact, the map can be written in this kind of list comprehension form. Instead of list map, we can say for x in L, return some function of x. Those two forms we have already discussed, and in fact, this can also be combined with filter. So I can say, for example, for x in 0 to, from 1 to 10, if x is divisible by 3, then I want to return x. So this corresponds to filter. But I can also say here yield f of x, and that would correspond to both map and filter. So in fact, this list comprehension operation can be used instead of any combinations of filtering, mapping, filtering and mapping, not reducing. Okay, now we have learned a lot, and it's time for you to try to practice. The problem for you now is to try to compute prime numbers in the interval from 2 to n. And you should probably know the algorithm to do that. If not, you can look it up on the internet. Ratosfin's sieve is the right algorithm. And try to define this function, which returns you the list of prime numbers in the interval from 2 to n. So it will take the n as the argument and return the list. Good luck with that.